It's a great pleasure to introduce you the speaker today. He's Dr. Tang-Kai Lee from the University of Columbia. He will talk about the asymptotic behavior of gradient flow solutions to PDE. Let's welcome him.
Thank you so much. Yeah, I'm very happy to have a chance to come back again. So I will talk about a problem that has a very elementary setting. Okay, and after introducing these problems, I will then specialize to a specific setting, starting from which there may be some more technical content. But at the beginning, everything will be very elementary, and you can ask these questions to many different equations. Okay, and please don't hesitate to stop me anytime if you have any questions or comments. Okay, I will appreciate all of them. The main result I will mention at the end is based on doing work with Jingze Zhu. Okay, so let me tell you the setting. Okay, the setting is about just ODE, so gradient flow. So let me write it in this way. So suppose we have a function which is C1, okay, and it is defined on an open set in a fixed Euclidean space. So for conventional reason, let me write it in. Okay, let me just write it in the simplest case. Okay, later we will specialize to the case when n is just 3. You can ask this for any function in Rn+1. Okay, so if you have a C1 function, then we will ask the solution to this ODE. So that is satisfy this differential equation. Okay, so as long as this f is C1, so that its gradient makes sense, you can ask the solution of this ODE. Okay, so this will give you the gradient flow line or gradient curve of this function f. Okay, so you can ask the existence and any properties of this gamma once you write down the function f. Okay, and we'll focus on the asymptotic behavior of such a gradient flow line when you have such a solution. Okay. Okay. So this especially means that if you have this, a solution gamma which is defined, say from time 0 to infinity, then when t is closer and closer to infinity, what can you say about the behavior of this curve? Okay. So let me formulate these questions first, and then I will draw some examples which may make things more clear. Okay, so the first question, okay, let me first take the definition. That is what is the limit point of such a flow line? Okay, so we say that point P is a limit point of a curve gamma. Okay, so this makes sense for any gamma, but we're particularly interested in the case when gamma is a solution to such an ODE. Okay, so this means that if you can find a sequence of time that diverge such that this P is the limit of this curve along this spatial time sequence. Okay, so this may not be a genuine limit. Okay, it is probably possible that if you choose a different time sequence, you will get a different limit. Okay. Yeah, but it's possible that there, for most of the that curve, you can find one limit point.
I'm sorry.
Yeah.
Can you move your backpack down?
Oh, okay. Yeah. Thank you. Yeah. Yeah, so this is the first zero order limiting behavior that we want to study. So let me write out the first question. Okay, I will call it the question by Hsuan-Yi. Okay, what he asked is about the uniqueness of limit points of gamma. So the question. So this means, suppose you fix the function and you find a solution gamma to this gradient flow line equation. Okay, so now you have a curve. The question is asking the following: if you know that there exists a limit point in this sense, okay, so there exists a time sequence along which you get this limit p. So the question is asking, is this p the genuine limit of this gamma t? Okay, so let me write it down. Okay, that is, if we have this t arising as a limit for some very special sequence ti, is this true? So we get a genuine limit. Which means that if you take any sequence of time, tj, which may not be related to this original time sequence you choose to define p, you always get a limit p. Okay, so this is the question. Is the question clear? Okay. So let me continue to mention another two questions, and I will draw some pictures to tell you why such questions may be non-trivial. Okay, so if we know that the answer to this question is yes, so if you do get a unique limit point, the next question you can ask is like higher order behavior of this gradient flow line. So limit point, excuse me, unique of limit points about the zero order behavior of this gradient curve. If you know this is unique, then you can talk about the direction of this gradient curve when it is closer and closer to this limit point. Okay, so this is related to a question asked by René Thom. This is the Thom who proved the Thom's transversality. Okay, so he asked the uniqueness of the limit sequence, which is one way to talk about the direction of the flow line. Okay, so what it means, so the following two questions is based on the fact that if the answer to the first question is yes. So now if you do get a unique limit point, then can you tell me that the direction, so by direction I mean this. Okay. So you look at the vector that is pointing from your curve to the limit point. So this gives you a direction, and we just care about the direction, not the vector. So you normalize it. Does this converge? Proper way to phrase this. Does this exist? Does this limit exist? Okay. Okay. So I think it's probably better to draw a picture now. So let me tell you some examples to illustrate why this question may be non-trivial. Okay. But before that, let me know if there's any questions or comments. Okay. So for the first question, okay, so the situation is, even if your potential function f is a smooth function, it is still possible that it has a gradient curve whose limit points are not unique. Okay, so the situation is, it is possible to construct a smooth function whose gradient curve looks like the following. Okay. It is in a finite region, and there exists a circle which collects all the possible limit points of this gradient curve. Okay, so you can imagine this white curve is still going outward every time, but is moving slowly and slowly and closer to the yellow circle, which means that if you fix any point on the yellow circle, you can always find a time sequence along which your curve along that particular time sequence converges to that point. As a result, this curve does not have a unique linear point. All the points on this yellow circle can be a linear point. Okay? So for the first question, even if you restrict to the class of smooth function, okay, the answer is still no. Okay? So this the answer to the first question, to the case when f is in general smooth, is no. Okay? So this is the first answer you can get from this picture. Okay? And so for the second question is, if your potential function is smooth, and if you do get a unique limit point, it's still possible that your direction may be changing all the time. Okay, so let me draw the picture for Tom's question. Okay. So the possible picture is a reverse picture. It's moving towards a fixed limit point. Okay, so for this picture now, our gradient curve has a unique limit point, but when it is getting closer and closer to this origin, its direction can keep changing. Okay, it just keeps rotating, which does not stop until it hits the limit point. Okay, so even if the answer to the Lavoisier's question is yes, and also your function is smooth, it's still possible that this limiting direction may not have a limit. Okay? So let me have the answer to this question. When f is smooth, okay, no. It's also no. However, okay, so let me tell you why I named the first question to be Lavoisier's question. That's because Lavoisier proved that this uniqueness is true when your potential function has stronger regularity. That is when f is analytic. Okay, let me write it down. If your function is analytic, Lavoisier proved that such a limit point is unique. Okay. Okay. That means, so this picture, the picture I drew here, which shows that it is possible when you are closer and closer to time infinity, your track can still move very slowly. This will not happen if your potential function is analytic. Okay? So Tom asked this question. In fact, he asked this particularly for analytic function. Okay, so his original question is, if your potential function f is analytic, then can you get a unique secant along this curve? Okay. So right now we know that this is also true when your potential function is analytic. So this is proved by Lavoisier. This was proven relatively recently by 3 mathematicians. Let me write it down. So it's not very important to our talk, but yeah, it's a very good result. So Kavika, Mostowski, and Rosinski. Okay, so that tells us that this picture, that when you are closer and closer to a fixed limit point, the direction can change very drastically, this won't happen when your potential function is analytic. So the much stronger regularity of your potential function can rule out this very weird behavior when you are closer to time infinity. Okay, so let me mention the final question, which is related to the second one. Okay, it is a refined version of the uniqueness of the limiting directions, and this is asked by Arnold. Okay, and the question is about the uniqueness of limit tangent of gamma. Okay. And as I mentioned, this also doesn't make sense unless you know that the limit point is unique. So this is also foolish. Okay, so if you know it has a unique limit point, can you say anything about the existence of the genuine moving direction of this gamma? You can see these are two related questions. In fact, this is a stronger version of these questions by Tong. If such a limit exists, then you can show that it will imply that this limit also exists. Okay, so, and because this is a stronger statement, so we know that this picture tells us that if your potential function is only smooth, then it's possible that your gradient curve can keep changing direction. Okay, so this is no. Okay, and for this, it's still an open question. Okay, so if you are bored by the rest of the talk, you can probably think about this question. Yeah, as far as I know, I think even when your potential function is only a general polynomial, this is also not known, which is strange. I mean, polynomial, but yeah.
Can I ask a question?
Yeah, please.
So in general, you say that if you don't have uniqueness of limit point, then it's the two limit, the limit of tangent may not exist. Is that what you mean? Is it possible that the limit of tangent exists, but the limit point doesn't exist?
Yeah, you mean this, right?
Yeah.
Well, yeah, right. So when your limit points are not unique, then certainly this doesn't make sense. But for this, well, this question still makes sense. But like it's hard to think about the meaning of it.
I see.
Yeah, right. For this picture of gold track, well, it does not converge to a fixed point, and also, I guess you can probably say that if the limit point is not okay. I think I can answer you. If you know that the limit points are not unique, then the limit tangents will also have more than one direction. I think if you have at least two limit points, then by I think probably mean value theory, you can say you can always change direction. Right. So you are right. Yeah.
But probably your limit point may not exist. I think in some cases it's possible that the limit, zero limit may not exist, but the tangent exists. That's possible.
That's what I was saying. What I was saying is that, like, if suppose your gamma has at least two limit points.
Zero limit point. No limit.
Oh, no limit points.
No limit.
Oh, okay.
To the straight line you're producing.
That's what I mean. Okay, I probably can phrase it in this way. If your gamma is in a boundary region, then probably not. Yeah. In a case when your gamma can, for example, as you mentioned, it gets to infinity. I think in that case, I think the uniqueness of the limit tangents may still be related to a version of this. But you probably, for example, if you can phrase this in the extended real plane, then probably that will, yeah. But yeah, but in general, yeah, if it's lying in an unbounded region, then yes, as you mentioned, it may happen. Yeah, that's true. Yeah.
Another question is it possible for the R0, the limit of tangent to be zero for it? Do we know it has to be non-zero? The limit of gamma prime divided by
zero. No, because I think you can thinking.
Can it vanish more than?
I think for example, if you have a gradient curve of a gradient flow line, I think it gamma prime won't vanish in finite time. I think.
I mean, if you divide it,
So I mean, for any finite t, this will always be a unit vector. I think.
Yeah, but the limit, can it be zero? Can the limit be zero, or it's unknown?
No. Let's see. Okay. Is it true? If this limit exists, then it has to be a unit vector.
Oh, yeah.
Yeah, because for each finite t,
Yeah,
is a unit vector. Yeah. Right. So if this limit exists, then it has to be a unit vector. Yeah.
Oh.
Right.
Right. Oh, I see.
Yeah. Yeah. Any other? Yeah. Thanks for the question. Any other questions or comments? Okay, then. Okay, let me tell you what I want to work on. Okay, so this result, for example, the fact that these Thom's questions can be answered for analytic functions tells you the following fact. So the corollary of this result by these three mathematicians, in particular, tells us that if F is a solution to a uniformly elliptic PDE, okay, and in this case, we know that F has to be analytic. As a result, their result tells us that then we have the uniqueness of limit points and limit tangents, limit seconds. Okay, this is one way to phrase the result. So the question that I want to talk about is what if F is a solution to a degenerate elliptic equation, okay, which is of course a more general class, and it also, solutions to such PDE also arise more naturally in physics and other fields. Okay, in particular, I want to know when your F does not have much regularity, because in these situations, your solution is automatically analytic, which is much stronger than a smooth function. So without this constraint, what can we say about the asymptotic behavior to a gradient flow line? So that's a question I want to ask. Okay. And before saying more about this direction, let me also remark why we also, besides its natural interest, why we care about the uniqueness of this gradient flow line. Okay, because in geometric analysis, when you phrase a problem in a parabolic way, they want to find canonical solutions, canonical shapes by some geometric flows. Okay, so most of them can be phrased as a gradient flow line of a functional in an infinite dimensional space. Okay. So you can add this uniqueness problem for those gradient flows in infinite dimensional space. Okay, so here this is the simplest version. Okay, and what I was saying is telling you, even in this simplest finite dimensional version, even in R3, even in R2, I think there are still some open questions that we don't know how to deal with. Okay. Okay, so now I'm going to a very special setting, okay, which is about this equation. Let me call it star. This is first write down, and I will explain why we care about it. Okay. 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 And from now on, we can focus on the case of three-dimensional space. So in the rest of this talk, I'll focus on this PDE, which is degenerate. Okay, so let me tell you why. Okay, if you expand this divergence, you will get two terms. First is the Laplace, okay, which is good. However, the other term is the Hessian of U in the normal direction of this level set. Okay, so this tells you that this is not taking the full trace of the Hessian of U. Okay, it does not contain the normal direction to those level sets, at least when gradient of U does not vanish. Okay, so this is not full Laplacian. This is a degenerate elliptic equation. Okay, so you definitely won't expect that the solution to such a PDE has much regularity. Okay, and it's true that we can find examples to show that it is not even C2. Okay, it's only C1. Okay, but what I want to study is those uniqueness questions. In fact, we can prove that they are still true in this very weak setting. Okay, so let me tell you why we study this equation. Okay, because it has some geometric meaning. Okay, so this is related to the next topic of this talk, is the mean curvature flow. Okay, so let me first tell you. Let me tell you the fact relating these two objects. Then I will give you a brief but formal introduction to this flow. So the fact is that if you look at the collection of level sets of U, which is a solution to this equation, then those level sets will be moving by the velocity given by the mean curvature vector of the level set. Okay. So the fact is, if your function solves this PDE, then its level set MT, so it's just the set of those points in R3, which is T, with function U. Okay, so this collection of sets is moving by the mean curvature flow. Okay, so what does this mean? Okay, so let me write it here. So that means this MT, so each of this MT, at least for short enough T, each of this MT is a smooth surface in R3. Okay, and if you look at the velocity of the position vector on this surface, it is just a mean curvature vector of this smooth surface. Okay, so this MT satisfies the velocity of the position vector is given by the mean curvature vector. So in the two-dimensional case, you can write this as the mean curvature scalar times the fixed unit outward normal. And this mean curvature is just the sum of the two principal curvatures. Okay. And the reason is that if you look at the defining equation of these smooth surfaces, you can run this equation as, okay, so now your x is moving So it depends on the time. Okay, so if you take a chain rule, you differentiate this in t, you'll get the direction of the gradient of u in the x direction, and that will naturally give you the information about the mean curvature vector. Okay, so let me not write this part down, but let me mention the examples, which may be more illustrating. Okay. So the first example is a round sphere. Okay, so the two-dimensional round sphere in R3. Okay. So this equation, probably is a PDE. Okay. It involves all the time variable and the space variable. Okay. But if you start this flow from the round S2, okay, two-dimensional sphere in R3, okay, this S2 has a spherical symmetry, which will be preserved by this PDE, okay, because mean curvature vector on a sphere is the same all everywhere. Okay, so this PDE can be reduced to an ODE to the radius function of this sphere. Okay, so we can solve that ODE directly and find that its evolution is just given by this. Okay, so if you start from a sphere with radius R0, okay, then along the mean curvature flow, it will just shrink and shrink to a point in finite time. Okay, so the picture is here. And because at any point the mean curvature vector is pointing inward in the same amount, okay, so it will shrink homogeneously. Okay, and when your sphere is becoming smaller and smaller, your curvature is also getting larger. So it will shrink faster and faster. So finally shrink to a point in finite time. Okay. And a similar example is you can use this idea to build a non-compact example. Okay. So you can imagine spheres are shrinking, so the round cylinders are also shrinking. Okay, so it will shrink to a singular line in finite time. Similarly, okay. So what I want to mention is that you can do this process for any surface, but a priori you may have some stranger shapes, okay, if you do not have any restriction on the initial surface. Okay. But if you know there are some spatial property of your initial surface, you can still get better convergence results. Okay, so if you start your flow from a convex closed surface, convex just means that each of its principal curvature is non-negative. Okay? So if you start a flow from such a good surface, so they will shrink to a point along the mean curvature flow in a finite amount of time. Okay. So this is just like this. Okay, so I can show a one-dimensional picture. Okay. It is, but initially your starting curve is in R2. So pictures of curves. Your curve may not be a perfect circle, okay, but it is convex, okay, which means at any point your principal curvature is positive. Okay, so when it's evolving, at any time it's not a perfect circle, but it will getting more and more circular. Okay, and finally it shrinks to a point. Okay, so if you look at the evolving curve very briefly before the singular time, you will get a curve which is almost the round circle. Okay, so it's a more general situation than the shrinking sphere. Okay. Any questions so far? Yeah, your question.
Is that that equation's power has the unique solution of two constants?
That's a very good question. If you fix the boundary condition, then yes. Yes. So let me write it down. Yes, that's a very good question and very important question. If you want to talk about more properties of this equation. Okay, so let me write it in a more precise way. Okay, thanks for the question. Okay, so let me write it in this writing. So the first is this questions in the let me fix U. This is a mean convex domain in R3. Okay. So this means that this is a bounded domain in R3 whose boundary is a smooth surface with positive mean curvature. Okay. So if we fix such a domain, then we will look at these equations in the interior of U. This equation. This is in U. And on a boundary, we'll just look at the derivative boundary condition. So U equals 0. Okay. So the result is that if you fix your mean convex domain and you fix the derivative boundary condition, then let me write it as a theorem. Okay. Star has a unique weak solution. So yes, if you fix the boundary condition. Yes. Any other questions or comments?
Is a mean complexity really necessary? In the general mean curvature flow case, we only have the flow limit.
That's true. That's true. That's exactly true. If you just want to start the flow, then you do not need to assume that your domain is mean convex. So the only reason why we impose this condition is that we want to formulate it in the lower set of a fixed function. Okay. Because in this case, your flow is always moving in one direction by its destination. Okay. So for example, if you're if you draw a non-convex curve, okay. So this is the curve in R2. Okay. So this part, when the convex is moving inward, when it's concave, it is moving outward. Okay. So then you immediately get out of the domain. Yeah, but you're right, if you just want to start a flow in general, if you don't care about its long-time behavior, then you can start the flow for any smooth domain, the boundary of the smooth domain. Yeah, that's true. Yeah. Any other questions? Okay, so let me now write down our okay, let me first tell you more properties of solutions to this PDE. Then I will tell you the main result. Okay. So when you look at these solutions to this degenerate elliptic equation in R3, okay, so first we know that solutions exist and is unique. We also know that the lower set of this solution will form the mean curvature flow. So now let me tell you the regularity of this function. Okay. Okay, I should mention the credit of each of this. So this existence and uniqueness of solutions to these equations was done by Evans, Brook, and Chen, Higa, Goto independently. Okay, so they developed a way to talk about the viscosity with the weak solutions to degenerate elliptic PDE and prove the uniqueness and the existence to such solutions. Okay, so we know solutions exist and are unique. Okay, then we can talk about their properties. Okay, so the first thing that we want to talk about is the result by Coding and Nicosi. Okay, so we know that this function, if you look at R3, we know that there has to be C1 in general. Okay. So the starting point here is that if it is a point at which your level set of U is a smooth surface, so you are at a point of a smooth surface, then this is not a problem. Your U is even analytic at that point. Okay. So the starting point is when your flow encounters a singularity, like this. So this is the singularity of the flow. Okay. So you may ask, although this is the singularity of a flow, but we do not have to care about it, right? Because it is also the time when your flow becomes extinct. But this is not a general situation. It is possible that your flow will develop a singularity before it disappears. So let me draw a picture. Okay, so this is an example that may be a typical example to keep in mind in the rest of the talk. So this is a picture in R3, so a picture of surfaces. Okay, so we look at dumbbell-shaped surface. So these two parts, they are very spherical, which are connected by a very thin neck. Okay. So if you arrange this surface in this way so that it is still mean convex, which is possible, then this thin neck, so you can see that because this is a two-dimensional picture, it's R2. So that cylindrical part has very large curvature. So it will shrink much faster than these two bells. They have relatively small mean curvature. So in finite time, the picture will become this. So this neck part will pinch together before these two spherical parts shrink to a point. Okay, so it is possible that a singularity can happen before the flow disappears. And those points are the points where this property becomes subtle. Okay, if you, for example, if you look at the regularity of U at this point, or at this point, there's no problem. Your U is smooth, even. They are analytic. Okay. So the result, the non-trivial part, the very deep part of the result is telling you even when your flow develops a singularity, your function U still has some very weak regularity. It's at least C1. Okay. So this is the first thing I want to mention. Yeah, is it clear? Okay. Okay. And what I want to mention is that this is the sharp regularity. Okay. For example, this picture. If you look at the, okay, I probably did not mention this. So this U, we will call it the Averrotan function of this flow mt, because it records the time when your flow reaches at that point. Okay, so it is the time when your flow touches that point. Okay, so if you look at the Averrotan function of this dumbbell, at this point, it is C1, but not C2. Okay, so you cannot get better results than this one. Okay, and moreover, they characterize when this Averrotan function is C2. Let me write down. Okay. Okay. So this U, it is C2 at a singular point T. This happens if and only if near this point, your singular set is a smooth submanifold. Okay. In this case, it's a smooth curve. Okay. Well, this is not very precise. So by this, I mean that this is a singularity, which is modeled on a cylinder. Okay, so exactly in this case. Okay, so sorry, this is not very precise. So what I mean by this is that this singularity. So briefly before this singular time, if you zoom in the region of this singular point, you will see almost cylinder before this pinching happens. Okay, so in this case, we'll call this singularity a cylindrical singularity. Okay, and the result says that at such a cylindrical singularity, your Averrotan function is C2 if and only if you get a curve. So in this case, we do not get a curve. We get a single point. Okay, so this condition is not satisfied. So this is not C2. Okay, so let me give you an example when this is satisfied. So another example in R3. Okay, so what you can imagine is you rotate a circle and get a very thin but rotationally symmetric and mean convex ring. Okay, so you take a circle and rotate it around a fixed axis, so you get a ring. Okay, if the radius of your circle is very small, you can still make it mean convex. Okay, so this flow will preserve the rotational symmetry. Okay, so it will finally collapse to a circle. Okay, so it will shrink to a circle. Okay, so now you see that it satisfies this condition. Okay, so at any point at a circle, you will finally collapse to a round circle. Okay, so each of these points, near this point, you get a curve. Okay, so your erode function will be C2. Okay. Any questions about this? Okay, so yeah, I hope that you haven't forgot our original 3 questions. Now I'm going to answer them. Okay, so let me write down the results. Okay, so let me recall the setting. So we have a mean convex, mean curvature flow. And such a mean curvature flow is associated with its arrival time function okay, so this just means that your U satisfies that equation and your MT is just the level set of this single function. Okay, so and we want to talk about the regularity at a singular point. Okay, so suppose P is a singular point of this flow. Okay, so one example is this one. Okay, another example is any point on this circle. Okay, so the result is that all the questions all the questions have positive solution, positive answer. Okay, so by all the questions, I mean the questions asked by Laura Sherwick, Tom, and Aldo. So all of these 3 questions, their solutions are yes, if first, if U is C2 at T. Okay, so this first result is saying that if you know that although you have a singularity, but if you know that your erode time function is still regular enough, it is not the worst regularity, it is at least C2, then you can show that it has a unique limit point, unique limit secant, and unique limiting direction, so the tangent. Okay, so this is the result by quoting them inequality. Okay, but you see, so there are examples that give you an erode function which has non-C2 singularity. So the result does not cover all the cases. In fact, this is probably a good place to remark. So these non-C2 points, these are points with lower regularity. They happen generically. Okay? Which means that if you perturb your initial surface, you can imagine in this dumbbell picture, if you move any part of this surface slightly a little bit, you can still expect to encounter the same type of singularity. Okay? So they are rigid under small perturbation in the initial data. On the other hand, these C2 examples, these high regularity examples, they are non-generic. You can imagine in this rotationally symmetric example, if you perturb, for example, if you squeeze any part of this measure ring a little bit, you can expect that part will immediately get larger curvature. So they will pinch together and then shrink to other parts. So the singularities won't be C2. Okay. So this result is a very good result, but it covers non-generic situation. Clear? Okay, so yeah, so I'm going to mention the one part. So the result that I did with Jingze 2. So we look at this regularity and these questions. When P is a neck cylindrical singularity, okay, I probably should have mentioned this earlier. So this is in general Euclidean space Rn+1. Okay, so you can do all the things we did in a general higher dimensional Euclidean space. Okay, and in those cases, you will have much more like different singularities. It may be modeled on, for example, in 5 dimensions, you can get 4-dimensional sphere and S2 cross R2. Okay, so if you still get a singularity which is modeled on these cylinders, but the R factor, the Euclidean factor, is 1. It is 1. Then we call such a singularity a neck cylindrical singularity. So this is an example. Okay, so in R3, if your singularity is modeled on S1 cross R1, then it is called a neck singularity. Okay. So we show that if your singularity is modeled on a cylinder which only has 1 R factor, you have uniqueness of the limit points, uniqueness of limit seconds, and uniqueness of limit tangents. You have all the uniqueness. Even at a point when your solution is not C2. Okay? So a corollary of this is that right here. Okay, so that general result in Rn+1. If you restrict to, I just erased in R3, because in R3, because you can only write 2 as 2 plus 0 and 1 plus 1. So in R3, you can only have either S2, and we know such an example is not very interesting because after this spherical singularity, your flow just disappears. Okay. And S1 cross R. Okay. So it's unlike the higher dimension case, you can have more than 1 R factor. Okay. So the upshot is that this covers all the cases in R3. Okay, for mean convex flow. In R3, okay, yeah, we get Lewis unique theorem for limit points and the Arnold-Tone conjecture. Okay, so the strongest statement about the equation X by Arnold is sometimes referred as the Arnold-Tone conjecture, and our result in particular implies that it is true if you look at any mean convex flow in R3. Yeah.
Could you explain the connection between the gradient flow and the setting of this problem? Because I don't know which concept is following the gradient flow.
Oh, okay. Yeah. Yeah, that's a good question. So let me clarify it. So, yeah. So what I mostly described was about gradient flow in a finite dimensional case. And so you look at the potential function in R, for example in R3, and look at its gradient curve. So in this case, our gradient curve are just gradient curve to the potential function given by this errata function. So for example, if you look at this picture, a gradient curve to this U will just be because this is just for a short time. So if you continue the flow after this singular time, you'll just get the flow line given by the mean curvature flow.
Okay. So it stops at the finite time?
Finite time, yeah. So in this case, all of the gradient flow, there was, okay. it looks like it disappears in finite time because this is using the time given by mean curvature flow. Yeah, let me write it down. Okay, let me erase this. Yeah, thanks for this clarifying question. Yeah, let me make it clearer. So our original question is about the. So now we look at U. So and what I was claiming is that if you look at the gradient flow whose potential function is given by this U, then its solution are just this flow line given by the flow. This looks pretty strange because we know that for such a gradient flow line, it always has infinite time of existence. That's true. Yeah, because if you switch to the time given by the flow, what you have to do is, so this is the first form, you have to reparameterize it. Okay, so in the mean curvature case, you have to look at the same curve, but with the different speeds. Okay, the reason why this is the more natural way to look at it is because this part is just the mean curvature squared. Okay. But they are just the same flow. Okay, so in this setting, yeah, if you use the original gradient flow framework, you will get a curve which moves slowlier and slowlier. So it will never touch this singularity in finite time. Yeah, but if you want to look at it more naturally, which is parallel to the flow, okay, and you do this change of variables, then you will get the one which moves parallel to the flow. Yeah. Does it answer your question?
Yeah. Thank you.
Yeah. Any other question? Okay, let me end this talk by mentioning why we want to look at such a spatial equation. Okay, so you may ask, this is a very spatial degenerate elliptic equation. So why do we, for those people who do not care about mean curvature, why do we want to look at those questions for solutions to this PDE? Okay, so the reason is that based on the results by those Kurdika, Mostowski, and Persinski, we know that solutions to uniformly elliptic PDE, they satisfy those equations. Okay? So the way is that we can probably change the point of view to look at which kind of PDE gives us solutions that have good unit property. Okay? One reason why this is probably a better way to phrase it is because we know that in this setting, you allow much worse regularity. Your solution may not even be C2. But we can still, if your equation has some good geometric meaning, that will allow you to use those geometric properties to get this unit property. Okay, that's the reason why we think that this is a good way to phrase this question. Let me stop here. Okay. Thank you.
Any questions for the speaker? You know that
Yeah, sure.
So in the very last part of your argument, you use the fact that the singularity model of the mean convex mean curvature flow is given by S2.
Yes. So yeah, that's true. So I did not mention this. So that's true. Yeah, I actually have mentioned this. So in general dimensions, if a mean convex flow, that all the singularities are modeled by generalized cylinders. So exactly as you say, they are of the form Sn cross R n minus k. So this was proven by Brown-White. Yeah. So in a special case when n is 2, so n plus 1 is 3, the only possibilities are S2 and S1 plus R.
So we don't have any conical.
That's true. No. That's true. If your initial surface is mean convex, which means that its mean curvature is positive, then no. That's true. Right.
So another question is, you say that C1 regularities. I was curious by coding in closely.
Yes.
Because the C1 and C2, they're in between probably C1 alpha. Probably if they quantize regularity.
Okay, so yeah, that's a good question. That's true. They're proven that they are C11. Okay. That's very interesting. So okay, let me mention this. So at this point, your your function is C1, not C2, but it is twice differentiable. Yeah, so it is twice differentiable at this point. So at any point, the Hessian exists, okay, but it is not continuous. Yeah, so it's C11. They prove that it is C1 and its Hessian is Lipschitz. So you get the best you can get.
I see. So there's no C1 alpha, but they actually get C11.
Yeah, that's very weird, but that's true. Yeah, yeah, right. Yeah, you get C11 but not C2. Yeah. Right.
Any other questions for the speaker?
So after you introduce the function u, that
Yep.
u is not related to analytic function, right?
That's true. Yeah, that's true. So if you only care about local properties, then for example, if you look at the flow at which your flow is smooth, then your u is analytic. In fact, at positive time, because the parabolic equation will regularize your flow. But at a singular point, then no. Right. So globally, it's not analytic. Yeah. So one of the thing I want to convey is that using this framework, you can even try to study those three questions when your functions may have worse regularity property. Yeah, exactly. Yeah.
Until the next lecture.